Hi, my talk today is about vision-based multi-MAV localization with anonymous relative measurements using couple probabilistic data association filter. My name is Ting Nguyen. I'm a PhD in computer information science. This is joint work with Dr. Kartik Morar, a former PhD and now research scientist at Auto Robotics. We are both under supervision of Dr. Kumar and Dr. Tyler at Penn. We will start with an introduction to multi-micro-area vehicles formation flight, followed by onboard sensing and computation for robot platforms that are subject to size, width, and power constraints. We then propose an extended couple probabilistic data association filter. The simulation shown to demonstrate state estimation and the formation flight control, before ending with conclusions. What is concerned here is a homogeneous team of autonomous micro-area vehicles that maneuver together in a disciplined, synchronized, and predetermined manner. We can see these systems are useful in performing tasks which otherwise may not either feasible or desirable to do with a single robot. For example, search and rescue operations, perimeter defense and patrolling, agriculture and construction. However, enabling these systems require to localize robots within a common reference frame. Third, each robot can execute its designated task, and the whole team can collaboratively complete the full task. How this is achieved in the literature? Well, one obvious solution is to use motion capture system or GPS, or assuming we have no known map or landmark, or assuming that initial position is measured, or using the relative measurements between robots with or without tags. However, all of these methods come with undeniable costs and drawbacks. The micro-area vehicles are FAV250. They are developed in Kumalab under DARPA Fast Lightweight Autonomy projects. They are 400 cm from tip to tip and weighs less than 1 kg. Because of their limitation in size, they are subject to size, width, and power constraints. Therefore, they are equipped with two types of lightweight sensor modalities: visual initial odometry using stereo cameras and initial measurement unit, and vision-based object detection. To overcome the hurdles in the literature, we propose an onboard sensing and computation. The idea is simple. We start with the perception modules. This provides us two key information: VIO and vision-based object detection. So one can provide us the robot cell localization, and the other can provide us the relative distance and bearing angles with respect to other robots. The estimation module then fuse the VIO with the relative distance and bearing angles, giving the robot poses in a common frame. By doing this, the control can be either open loop or closed loop. More importantly, no external sensors are necessary. No GPS, no motion capture system is required here. State estimation. This is a key component. What are the challenges? Well, object detection can yield false positives, false negatives. Detections are also anonymous in a homogeneous system because all robots look the same. Therefore, hard assignment algorithms can cause diversions. No static observer. Each detection actually depends on the state of multiple robots. So, joint probabilistic data association filter, which assumes all observations are independent, is not an appropriate choice. Relative measurements derived from object detection is nonlinear. To overcome all of those challenges, we propose an extended couple probabilistic data association filter. System state. Remember that for a given robot, there are two kinds of motions. Its motion with respect to its own frame and its motion with respect to a common moving frame. Moreover, in an extended command filter framework, there's four unobservable parameters. Therefore, we represent the individual robot state by the four components its position and yaw in a moving common moving frame, and the transition and yaw of its moving frame in a common moving frame. We then couple every single individual robot state into a single vector representing the system state. And assuming the constant velocity model, we can represent the system state equation as shown here. Other models include odometry measurement model, detection measurement model, false positive distribution model, and the noises are explicitly modeled based on the real-world data for the simulation experiments. Here is a flowchart of the filtering process. Like that of other common filters, it also starts with prediction. When detections come, we use gating to ignore ones that fall out of the confidence bound. The first difference lies on evaluating the hypothesis. Note that each robot can detect other robots using different measurements. Therefore, there can be many possible matchings. And the second difference lies on how to update the detections. Imagine in one system, one robot can detect other three robots, target 1, target 2, and target 3, and using the measurements without any ID. So what we do is to create a hypothesis tree whose levels are robot targets, the nodes representing measurements. A path connecting the root to all levels with no repetition would be an assignment hypothesis. And the hypothesis evaluation, what it does is other than enumerating all possible assignments and then in computing the likelihood for each and use the information to estimate the posterior of the system state. As mentioned, in the detection update, we use the likelihood of a hypothesis and corresponding innovation to update the system state. Time complexity. The dominant factor is the number of hypotheses, which sadly can grow exponentially with respect to number of robots. So a possible improvement is to use k-based hypothesis algorithms, which can bring down to polynomial time. Let's move on to the experiments. The first one is to compare the performance in state estimation between our approach and the naive ones, which is basically the integration of VIO. We set up a raw simulation with 6 robots whose measurement model noises are derived from the real-world data. We then use the graph truth poses to drive the robots around and then report the errors between the estimate and the graph truth in both approaches. We quantitatively evaluate the performance of state estimation in two folds. On the two figures, the x-axis shows the time while the y-axis shows the MSEs of the errors. The left figure shows the errors with respect to the common fixed frame. The right figure shows the error with respect to the common moving frame. As you can see, when it comes to absolute state estimation, two approaches perform comparably, and that drift were due to the cumulative VIO noise. However, when it comes to relative state estimation, our performs better, and more interestingly, the error does not increase over time as that of the naive approach. This suggests that ours is better at maintaining the spatial configurations. Now we want to put all together to perform a simulation on formation flight control using the estimated state. This simulation, developed in Rust and Gazebo, demonstrates the formation flight controls of 6 robots. Measurement noises are modeled based on the real-world data. Due to these noises, the measurements are inaccurate and so does the state estimation. Purple ellipsoids represent the state estimation variance in X, Y, and Z. As expected, the state estimates are off on the graph truth, but all spatial configurations are well performed. Conclusions. Our onboard sensing and computation enables multi-MAV formation flight using only cameras and AMU. We propose an extended couple probabilistic data association filter to handle anonymous and noisy relative measurements. The experiments on simulation demonstrate the superior performance of the filter in correlation with the VIO only. Future directions include improving the hypothesis evaluation step and deploying on the hardware systems. Thank you for listening.